digital communication part. So ideally, we would require a lot of classes to finish off the content that is left with us. But we actually have primarily 10 classes, including today's class. So the content is pretty high, but the time is very short. So that's why, in some cases, I would focus on the most important segments that is relevant, and the rest of the things I'll upload the materials and which you need to do a self study, and that will be the mode of operation. And if at all time permits, I will take some extra classes to furnish all the other details if necessary time, like everything is in our favor. All right. So let me quickly start off with and that's why primarily I would focus on some presentation, as you know that will save a little bit of time. Although to be honest, I don't really like to present as such. I feel it's pretty boring thing to do this presentation and all. But I need to, because I need to finish portions as much as possible. All right, so let me start sharing my screen, and you please let me know whether you are able to see the screen. All right, so just let me know if it is possible. Can you see the screen over here? Because I'm using the web browser, so I don't have the option to check it actually. Is it visible to all?
Yes, sir.
All right. So today we are going to start with the fourth module, which happens to be the digital communication part. We have discussed the amplitude or the analog portion in before the CAT2, and so let us quickly find out that what is the digit. Why do I need a digital transmission and requirement? Like subsequently, so the first thing is that whenever a message signal is generated, okay, and that can be an analog source or a digital source, uh, that if the message is derived from a digital source, okay, just like a computer or the way that we are talking also, these are all digital in nature, okay, and that has some inherent advantage. We'll come to that advantage also, and that is primarily the reason why people are more inclined toward digital techniques, as much as people are getting obsolete. The analog techniques are getting obsoleted by now. So even the thing is that whenever a message, it can be a speech or a video, which the speech signal, as you know, that is an analog signal actually, but that can be converted into a digital form in a way, so that the device are compatible to understand this. Okay, for example, Alexa is a very common example of it, where you dictate it, or in a Google also you will just type, or you will just speak something, and it will decipher that what exactly you are searching for, right? So that basically is a digital conversion that is taking place. So this particular module that we are going to discuss, this will touch upon points on how the digital mode of transmission would take place if you are looking at uh, uh, in terms of communication engineering, because as in the DCS, or the digital communication system itself, it's a subject altogether. So that you can understand that how the total, the gravity or the total depth of a subject, that it's a separate subject altogether. But in your course, it's basically touching upon points on digital transmission. All right, so in that, one of the very key important factor that we have to discuss, we'll come to that again later, but at least for this slide, is the third point, where the sampling process is the first process which is performed in an analog to digital conversion. Okay, so what exactly it is, we will see that. And the other two, which is the quantization as well as the encoding, uh, that also soon will be followed. Some of the conventional techniques which we are going to study is the pulse code modulation, the differential pulse code modulation, the delta modulation, the adaptive delta modulation. So these are some of the key techniques. In fact, these four techniques are the key to the fourth module itself. Okay, so in that's the whole portion of it. You can check the syllabus also. So this is the portion. But again, on all each individual topic, that itself is a depth topic. So we will again, I will specifically focus on areas which is important from your side. So if you remember that we had started discussing our PCM, where this particular course with a block diagram of this nature, and I told you that the structure will remain almost the same even when we look into the digital transmission. And that's mainly because that if you observe carefully, that in this particular diagram, The information source is what we start off with, which is basically the input that we are giving, right? Now that can be an image, that can be a video, that can be an audio, this can be a speech, this can be anything, right? Now that is needs to be reformatted in a way. So if you observe carefully that in some of the blocks which are like this, the shaded one, okay, so these are given as an optional element. So this, although it is called as optional, but they are very much used in most of the digital transmission. Although we will not touch upon this directly, as I said, it will. I just wanted to give you an overview of the transmission and the receiving scheme. So you can observe that there are source encoding technique, which is over here, say source encoding technique. Then we have an encryption block over here, where the data might get encrypted. Source encoding is basically where you are repetitively sending a data, and if at all you are making a mistake in the transmission, so there will be a retransmission somewhere, okay, and it will be corrected. So that's kind of thing will happen. Encryption in general, I think all of you at least have the understanding of the term encryption. It's basically where you're hiding the information so that it is unique. Okay, when we are talking, suppose we are talking now in a class. Now this is a kind of a one-to-one communication we are doing. Now suppose if it is not in that way that anyone can listen to us what we are talking about without even joining this meeting, then it basically you are making a false statement with the privacy. All right, so that is a very, very important aspect of today's world, that encryption should be very high. I guess all of you have heard, at least all at least are familiar with the term of WhatsApp and Facebook and the data piracy and the data encryption. What happened, the data getting leaked to the internet and all those things. I guess these terms are very common to you. So this encryption is very important. That's why the data needs to be hidden from the attacks. And then we have a channel coding over here, that is basically where that how the data can be, the encapsulated data, that is the hidden data, can be made in a way such that it can be transmitted over the channel. Now this channel can be again an optical fiber, it can be a wireless channel, it can be a wired channel, whatever you call them. Okay, so that is another thing. Then you have the multiplexing. Now this multiplexing, we haven't discussed anything as such, but we will, when we look at into, I think, sixth module most probably, we will touch upon this multiplexing sometime, some portion, where basically where multiplexing is a technique where you actually are squeezing in more and more information in a small little dimension. So you can imagine, just think in a way that as if that you are in a class. Okay, you are in a class and there are 60 students out there. Now suppose I make an arrangement such that at a given point of time there will be 30 students in my class, while the 30 will wait in a lobby, and then again the 30 will come and join in, and the other 30, the previous 30, will wait, or they will be assigned some other task. So what we are going to do, we are basically multitasking the process or multiplexing the process. And what I am trying to do is a time division multiple access, basically. That within the same time slot, I am allotting 30 students for doing some work, and the rest 30 I am allotting some other work. And then we are switching over. So if you imagine in that way, that is basically a multiplexing. What happens is here that within a short span, like it can be a time. So this multiplexing can be like time multiplex, it can be again frequency multiplex, it can be space multiplexed. Okay, it can be orthogonality can be maintained. So many different techniques are there, but ideally the advantage is that in a small time duration you can accommodate many number of users. In a small frequency bandwidth, you are allotting many number of users. Within the user, you are making an arrangement such that they are not interfering amongst each other, right? So this kind of things can be done using multiplexing. What is the advantage of it then? That if we are doing such a multiplexing techniques, and if at all if it is correct, then basically we can improve our data rate, bit rate. Okay, I guess I'll tell you that about next slide only. But ideally that is one of the very important factors of digital transmission. I'll come to that, what are the factors involved with it after this. But if you observe carefully, that this is where the pulse modulate will come in, which is the PCM I was telling you, the PCM kind of thing that we were talking about. Then we have the band pass modulation, Okay, so this is basically where the modulation is actually taking place. Just like the amplitude modulation is there, similarly we can have a digital modulation scheme as well. But in case of analog modulation, it was more of a continuous signal that we were processing, whereas in case of digital modulation, we are going to process the sample signal or a discontinuous signal, you can say in that way. All right. So along with that, there can be some frequency spread spectrum. This comes in the seventh module. In fact, we'll discuss that there itself, that how we can make an unique arrangement such that each and every user, when they are sending the data, they will be unique, and so that whenever it is transmitted over this channel, this part, okay, it will be, if even if someone tries to disturb it, it will be an encapsulated one, and it won't be affected, or rather it will be less affected by the environment or the noise. Okay, so this kind of many complex thing comes in with respect to digital transmission. But eventually what happens, the output that we are getting, that is input and output, you can see the message symbol over here, and we are getting the digital output over here. This digital output is much refined quality to that of the analog signal. All right, so that is basically why we are looking at, or we are rooting for the digital transmission technique. So ideally, in concise form, if I call it, the transmitters modulate the analog messages or bits in case of VCS for the transmission over a channel. Receivers will recreate the signal or regenerate the signals or bits from the received signal, and it will mitigate the channel effect as well. Okay, so that is where the channel encoding techniques will help. And there are performance metrics such as the bit error rate or the probability of error. Those things will give us an information about the how better is the system, how well the system is working. All right, so that is basically what the different techniques or different requirements for digital transmissions are. As I already had pointed out some of them, it's the primary advantage of digital transmissions is that easy to regenerate the distorted signal. That is one of the biggest advantage of it, because in case of analog signal, what happens, the noise, the whenever you are sending the data over a channel, okay, the signal will get corrupted by any, like such a mean that it's very difficult to reconstruct the signal at the end. Although we have discussed the different transmission and receiving techniques in case of analog transmission, but eventually that will be really, it won't be really helpful for that matter. Okay, so that's why we need to take it into account, the digital transmission. And that is why the one of the reason is that it reconstructs the signals pretty well. Okay, and that for that purpose, regenerative repeaters are one of the blocks or modules which is usually used, where a new clean and noise free signal, it's you can see that the repeaters prevent accumulation of noise along the path. So that noise immunity is a super advantage of any scheme, because that deteriorates the signal in a big way. So that's why in case of digital transmission, it has an inherent advantage of having a noise immunity. The second is input to a digital system is in the form of sequence of bits. So it's not a continuous sequence, it's a discrete sequence. So you will call it like 6 bit at a time. Suppose I call it a system which is a binary signal. Suppose it's binary signal. Binary means 1 or 0. So basically we will say that 2 bit at a time is the transmission rate. Simple as that. If there are 4 bits at a time, we'll call it the quadrature phase shift key. Okay, or if it is a more than that also, we can say that. So this m, you can see m is a general term, so it will depend on the number of bits that is going to get transmitted. All right, so that is why we call it the binary transmission or binary data transmission or m array transmission in general. And that also has the advantage, the modulation scheme. This is with respect to the sequence of beats, and when it is get modulated. So in that aspect also, the immunity is very high with respect to distortions. This is, we are comparing with respect to analog systems, to be honest. Okay, so with respect to that, it's better. It's not that there won't be any distortion, there won't be any interference, not that. Okay, there will be some, but that can be prevented to a certain extent. Naturally, the hardware is more flexible. Okay, that's primarily because the more the digital techniques came in, the mini processors, the VLSI techniques, the small little chips, those were affordable and being has been used. And that's why you can see, the since it has a very short duration of design cycle and the production cycle, so lots of uh, circuit elements or the components can be generated, and that's why the overall costing comes down. That's why you will find that a digital meter and an analog system will have a huge difference in the costing as well. Even the equipment that you might have purchased will have lost less cost as a digital system if you compare to an analog system. All right. So that is another advantage. Digital multiplexing is much easier than analog. Already, I just have told you. Using digital technique, is it possible to combine both the format for transmission through common medium, which is means that suppose I am speaking now with you, so that is speech media. So basically, my voice is getting converted somehow in an A to D conversion, and then the data is being fed to you. Again, there will be a regeneration where you are able to listen to what I am talking right now. But again, now suppose I open my video cam and you are looking at my face, or I'm doing a live streaming, so that's basically the video is being processed again, right? So at the same point of time, the speech as well as the video both can be processed together, and that is one of the salient advantage of a digital transmissions advanced scheme. Okay, that is not very easily can be done in analog system. The next part is the encryption, very, very important. In fact, the encryption and privacy was the main advantage of why the mobile communication or mobile telephone system became so popular at some point of time. Because when the you, I guess all of you at least have heard the term GSM, like the 2G phone. For you, it will be better for if I use the word 2G. So the 2G SIM card, when we used to have the Nokia phones, the previous generation phone, you people might have not seen it, but like back in 2005 4 like that, when first in the initial advent of mobile communication, it was a 2G device, right? So that 2G device, why it became popular, because that has an inherent advantage of encryption and privacy, and that was primarily because of digital techniques coming forward in making advancement in the all fear of technologies. All right, so even in this is very crucial for our system. All right. All right. All right. We so these are the basic requirements for any block, if you call it, that to maximize the transmission rate at the time. Based on that, we will have to utilize the system utilization. Okay, the maximize we have to maximize the utilization, but in the context we have to minimize the bit error rate, which I told you as one of the performance matrix. We have to minimize the bandwidth requirement, because the lesser bandwidth you want to provide for the user, and you can accommodate more number of users in that small bandwidth, the better is the revenue collection. Because in digital system, the one of the most, remember this at any point, one of the most important factor that governs a digital system is the bandwidth. The Any system that you are developing, if it requires less bandwidth, okay, it will be better. That's the thing. Okay, you suppose you create an app. Okay, you create an app, but the app has a very huge size, it won't be acceptable. Okay, you create a process of some techniques for that matter, where you can accommodate thousands of users. Okay, instead of only accommodating 10 number of users, the 100 users accommodation on the system of that nature will be accepted. Okay, so bandwidth is a very important factor in digital transmission. Along with that, to minimize the complexity, because as I already showed you the block diagram, that itself it's a complex system. We can't make it more complex. So keeping the minimalist complexity in the hand, we have to make the adjustments. That is why the digital signal processing, digital image processing, and other digital techniques will come into handy, because where only focus is given on the processing part, so that we have the system, and we will make sure arrangements are made or algorithms are tested such that the processing becomes easier. Okay, so that is basically the option. And also to minimize the required EB by N naught, because in that way we are reducing the noise factor that is coming in from the system. So these are the primary advantages of the digital over analog, and the necessary adjustments that we have to keep in mind. This is some of the nomenclatures which are very common to digital systems. I thought of just sharing it with you. Unfortunately, this part is getting highlighted. But anyway, for one is a digital message, as I said, like it can be binary ones and zeros. So all the data, whatever we are talking, in fact, I'm speaking, this is getting converted to some kind of a 1010 pattern. and that has is processed. Okay, that is speech. The speech signal has been processed and is being shared with you. Okay, so that is basically digital message. M array, I already had told you that how many number of bits that the symbol is constitute. Suppose there are 4 bits that constitutes one symbol, so then we'll call it the M array. So 4 will be quadrature array, kind of, you can say. Okay. Similarly, digital waveform and bitrate. Bitrate is, as I already said, that it is an actual rate at which the information is transmitted per unit time. So it is like how much is the data rate in that way. Data and bitrate and all those things are coming in because we are considering one or zeros as the main source of our information. Baud rate is common to people who have already used the microcontrollers, or for example the Arduinos and all. You might have found out the baud rate. So baud rate refers to the rate at which the signaling elements are transmitted for that particular device and all. So number of signaling elements per second. So that's given by the baud rate. That again depends on the specification of the device that you are going to use and all. And bit error rate, very very important thing. BER we call it in short. Bit error rate is a probability that one of the bit is in error, or simply the probability of error. Okay, so suppose you are sending thousands and lakhs of data, okay, and or rather transmitting bits, if I call it, and there is a huge probability of error or huge bit error rate, then basically we will assume that the system is corrupted. So we need to make sure that the bit error rate or the probability of error will significantly come down, or how we can make it come down at a certain pace. All right, so that is basically the system that we are talking about. So now at least I think all of you have at least have an idea of why we are focusing on digital systems and digital transmission. What are the advantages of it, and what are the parts of it, to be honest. And as I said on the very first slide over here, if you go back over here, the first thing that comes into mind is the sampling process. That is the absolute starting point of any discussion. So let us discuss about the sampling process and how it works. So ideally, the sampling theorem, there is a very important theorem which is called as the sampling theorem, which says just for the following, and you can see from the graph itself that if a continuous time signal may be completely represented, read it very carefully and keep in mind, because this is the fundamental of starting of digital communication. A continuous time signal may be completely represented in its samples, okay, and recovered back if the sampling frequency, please make a note of this, if the sampling frequency fs is greater than equal to twice of fm. Okay, where fs is the sampling frequency and fm is the maximum frequency present in the signal. So if you closely observe this particular diagram, that this is a continuous time signal, okay, time signal, GT is a continuous time signal. What we are actually doing, we are getting some kind of a sampled signal over here, and they are all impulses. You can observe that there are impulses. So in between there is no, in between there are no samples present. So basically it is like you are just picking up some data points or some sample points from a continuous signal, and you are regenerating, you are assuming some kind of a form that the original signal used to have. Naturally you might have an argument, or you might have a doubt that, sir, when we are assuming that we are assuming us, or we are recreating a sampled signal, will not be that there will be some error that will be introduced, because the original signal is something and we are taking some samples. So does the sample will exactly recreate it? That is what we are talking about, the sampling theorem, that yes, it is possible if we keep the sampling frequency to be of twice of fm. Simple as that. We actually can do it, and that is clearly mentioned over here in this particular diagram. All right, so if you observe that this xt, which is in the frequency domain, will have a plot of this nature. What we are trying to do, we are basically using a multiplier where we are sending a train of pulses over here. This is an impulse train, okay, or we call it the sampler. So this is basically the band limited signal. So this is the band limited signal, okay, and this is the sampler. So sampler is basically an impulse train that we are looking at, and this sampler, if you get multiplied, you can observe that clearly it will be something like this. It will go on like this, as if, okay. So it will be like this, like this. All right. So that is like basically you are looking at over here. All right. And you can also observe that keeping this condition fs greater than equal to 2 fm, what we are achieving, that one is that we are sampling the data. So hopefully all of you are clear now about the sampling, why we are calling it as a sample, because you can see that since it's an impulse train, between these 2 points, this particular segment, suppose I'm pointing out, we don't have any data. So as if there must be some process, that is basically what the quantization and encoding will tell you, that by some process we are actually regenerating, as if we are assuming that what should be the envelope pattern of the signal. All right. So that is ideally the advantage of having the sampling process. So if you are considering this particular condition fs greater than twice fm, you are observing that in the frequency domain there is no overlapping that is taking place. If you observe carefully, that there is no overlapping between the samples over here. I'll tell you separately about this, but still, since the diagram we are discussing, so you can observe that clearly there is no overlapping that is taking place, and that is called as the aliasing error. We'll see that sometime later. But ideally, if you keep the frequency of sampling of this nature, there won't be any aliasing. So the term is aliasing error, or you in simple word, it's basically an overlapping in nature. So that ideally will make us believe that if I consider in this way, okay, as long as there is fs greater than twice fm, there would be no overlap. And if we pass the y3 to a low pass filter, even the bandwidth of 2 fm, then signal can be recovered back as well. So just remember this very carefully. All right. So I thought of just sharing few points before we move on with the next one. So let me just quickly go back to my new notes. 1 minute. Yeah. So let me just show you one very small little derivation kind of thing, so that at least you guys have an idea about it. So let us assume that xt, okay, xt is the band's limited signal that we had already discussed. So it is a band limited signal, okay, and we have sigma tau s, okay, this is given by the sampler, okay. So as we all know that fs, we have already defined that this is a sampling frequency, or we call it the rate of sampling, okay. And or sometimes we call it 1 by if I consider 1 by ts, if I consider, that will be sampling rate, okay. This is sampling rate, but whatever, this is not that relevant as of now. So what we are trying to do, we are actually multiplying it, right? So this is xt multiplied by sigma tau s t. So this is basically what we are trying to do. Okay, now this impulse response that we are talking about, the sigma tau s, this one, this can be separately if I write, okay, it will look something like 1 by ts 1 plus 2 cos omega st, okay, plus 2 cos 2 omega st, and so on and so forth. So like that, it's a, this is the nature of it. This is called as a, this is the nature of the impulse response, and it's a Fourier series expansion of impulse response. Okay, we don't need to focus on that much, but what we are going to do, we are going to multiply this. If you observe carefully, we are just multiplying this by an xt. So what will happen in gt, it will be 1 by ts, and then xt gets multiplied. So xt plus 2xt cos omega st plus 2xt cos 2 omega st plus dot dot dot, like this. All right. Now if I take the Fourier transform of this, okay, that is in the frequency domain, if I consider, so g omega, this becomes after a certain let me just do that as well, so that at least you have an idea. So ideally this will happen 2x of omega, omega minus omega s, actually this will be omega minus omega s, omega s plus omega, sorry, x of omega plus omega x, it should be x omega plus omega s. So one will be the minus, one will be the plus. Then you have this 2 should not be there actually. Plus x of omega minus 2 omega s plus x of omega plus 2 omega s. Like that it will go on. Okay, it will go on as a series. And if I go on as a generic expression, so g omega will be given by 1 by ts summation of n it tends to infinity x of omega minus n omega s. All right. So this is ideally what we will do. Now, what is omega s? Omega s is nothing but 2 pi by ts, or where fs is also equal to 1 by ts. So like that, it is 2 pi fs basically. It is 2 pi fs. So one, this is all we know. Now, if we have to reconstruct xt from this g omega already I think you have seen over here. This is basically the g omega over here. So I have just made the expression to find g omega. So this is what is being plotted over here. So if you want to reconstruct xt from gt, that is we have to extract x omega from this g omega. Okay, it is clear that if I consider fs greater than equal to twice fm, that is the sampling theory or the sampling formula, that is the only way it is possible to generate the x omega from g omega. So g omega has x part. So if I want to reconstruct means the receiver I'm talking about, it can only be possible if we have sampled it in the transmitter with an fs greater than twice fm, and in the receiver we will reconstruct the signal without any overlap. All right. So that is basically the mathematical model of the same, and in that aspect. So in that way, in that aspect, if I go back to this point, or maybe what I'll do is I'll just write it down over here itself. So this fs greater than equal to, you can observe here that if it is fs equal to twice fm, this is the minimum condition. Please carefully observe, greater than equal to is the best condition, but fs equal to fm is the minimum condition or the minimum sampling rate for which the overlapping will not occur. So this is the minimum, please make a note, minimum sampling frequency fs for which no overlap will occur. And this particular condition, fs equal to twice fm, is called as Nyquist rate. Very important factor, Nyquist interval, Nyquist rate. This is called a Nyquist rate. Okay, for any sampling, Nyquist rate is the minimum rate that you can consider. It cannot be that, because even after this, it will be under modulation. We call it the under sampling rather. I'll tell you that also. And Nyquist rate. So Nyquist rate will be simply 1 by 2 fm. So this will be Nyquist rate of considering S prime, suppose I call it, because already we have defined Ts. So Nyquist, sorry, so this is Nyquist interval. Sorry, I'm sorry. This should be Nyquist interval. So one is, we call it the sampling rate. So this is Nyquist interval. All right. So one is called as the Nyquist rate, which is Fs equal to sampling rate is equal to twice Fm, for which the overlapping will never happen. And same way, if I consider it in a time domain factor, or if I consider represent it in a time, it is basically Nyquist interval, we call it. And the sampling frequency, the best condition is Fs greater than twice Fm, for which no overlapping will take place. All right. And if you consider the other way around, that as we have already like seen the very similar kind of thing in an analog system as well, that if the condition, if it is Fs, okay, if it is fs twice of fm, okay, if this is the condition that we are considering, then definitely there will be a chance, there will be a case where we actually have an aliasing. You can see this diagram particularly. So you can observe carefully that this is a condition where fs is less than twice fm, and in this particular case you can see that there is some interference that is taking place over here. This is the interference part, and we call it the aliasing error. All right. And aliasing happens primarily when the high frequency component of the signal takes the identity of the lower frequency component. Just remember this carefully. So aliasing happens when higher frequency component of signal, okay, takes the role of low frequency signal. So what will happen eventually, that if that is happens, so the system will identify, okay, the system will identify that it is a low frequency signal. Now usually, if suppose you are using a low pass filter, so the low frequency, the high frequency signal which has been considered, which has like is imitated as a low frequency signal, will be passed on. So basically this particular noise, this is noise, okay, that's interference, will be carried forward. All right, and that will eventually add up to the process of detection error at the receiver. All right, so that's why this is not advantageous, and in fact this is a interference also, in a way that if you observe carefully, that if suppose any one lobe, if you consider the data which was there over here in this particular shaded region where I'm actually shading right now, they are actually corrupted. So there will be a lot of, if you consider this particular shaded triangle, a portion of this A, suppose I mark it as A, and this portion as B, so both of them are suffering over here. Okay, so that is not acceptable, because that is the loss of data. All right, so that is to be avoided, and that is why what we usually do is that the signal is first passed through a low pass anti-aliasing filter. Okay, and to the whenever it is passed through a low pass anti-aliasing filter, what will happen, that the high frequency component will be eliminated. So before it converts to a low frequency, because before it gets makeover with a low frequency signal, it is eliminated, or the signal is carried forward, only the low frequency is carried forward, and after that the sampling takes place. So if you go back, I think I don't have the block diagram over here, but I'll show you next day, where you will find that there will be a low pass filter or a low pass anti aliasing filter, which will be specifically placed before the multiplier. All right, so after that only the sampling process will start, and that happens because of the high frequency signal. So if you just if this is clear up till this point, is it clear? So this is all about the sampling part. Anyone having any doubt with this? Please tell me, let me know. Anyone? All right, hopefully you got the idea. 29 odd people are there. So is there anyone having any doubt till this point? What is sampling? Why we are doing a sampling? What is the final outcome of a sampling? Hopefully this is clear to everyone or one of you. So let me just take a small little test of yours, so that I can be assured that you are able to understand. So suppose you have an analog signal, okay? So you have this is just a numerical small little example, I call it. So if suppose you are given an xt, okay, that is given as 3 cos of 50 pi t plus 10 sine of 300 pi t minus cos of 100 pi t. Okay, so suppose this is a signal, analog signal given to you. Question is, calculate the Nyquist rate and the Nyquist interval. So calculate Nyquist rate and Nyquist interval. All right. So if you observe carefully, can anyone tell me what will be the first thing that should be noted over here? What you are looking at over here, and you can find me that what should be the approach? You have to find out Nyquist rate. Okay, so Nyquist rate is nothing but Fs equal to twice Fm. So we can get it. Okay, now this is a modulating signal. You can see xt it is given. So what should be the Fm? Can anyone tell me? Can anyone please tell me what should be Fm if the xt is given like this? No one?
So the highest frequency term.
Highest frequency term. But the problem here is what I think all of you might have seen, that about, so let me write it once. Okay, so the three frequency component over here is 50 pi t, one is 300 pi t, and 100 pi t. So these are the three frequency component which is present. But remember that we are representing this in terms of omega. So it's omega t that is given. It's not that ft. It's 2 pi ft, right? So this is omega 2t or this is omega 3t. So that means this is equal to 2 pi f1, 2 pi f2 and 2 pi f3. All right. So eventually what I mean is that your maximum frequency if I calculate as f1, so f1 will be 50 by 2 pi, or rather if pi gets cancelled over here, so 2 by 50, so sorry, 50 by 2, which is 25 hertz. Okay, f2 will be 150 hertz. Okay, 150 hertz. Okay, and f3 will be 50 hertz. Okay, so this small little information you need to understand carefully. Okay, we don't consider the frequency which is given over here as fm. That is the main objective over here. Okay, so this is 2 pi f, so from that we can get it. And as it was rightly pointed out, amongst f1, f2, f3, which one is the maximum? So maximum frequency fm is about, this is 150. This is 150 hertz. So your sampling frequency fs is 2 fm, which is 300 hertz once again. So this is basically the condition. And naturally, this is also, we call it the Nyquist rate, and the Nyquist interval will be nothing but 1 by 2 fm to 1 by 300, which is around 3.3 milliseconds as an answer. So like that, you can observe that this, if I consider, if for an analog signal, if I consider sending this data, we can actually have a scenario where we are looking at a digital form of this particular signal, keeping the aliasing part from our equation. All right. So this is about the sampling and its process. So let me just show you that what exactly is quantization, that is after what is sampling, what we have done, what will happen after that. Okay, so should I do this or should I stop at this point, because I need to show you another diagram which is missing over here. I'll just see whether it's somewhere. I think it is there. Where is it? Yeah, it is there actually. So if you closely observe, I'll show you this diagram, and we'll start off from next day itself from here. So this is my xt. All right, this is my xt which is present right now. After the sampling is done, we are into this. So we now know why it is sampling, how it is sampling, and what are the discrete points that we are getting. Finally, after this, the quantized signal will come in. Now, what is a quantization? Quantization is to fix. You can observe that each of this impulse that you're looking at, they form a certain level over here. If you consider each of them, each of these points, for example, I'll just roughly, I'll try to do it like this. If you take this, so there is some portion in the y-axis which has a level. So in quantization, what happens is that after we get the sample signal at different time instance, the magnitudes are also noted. Okay, and all these magnitudes are given a particular level. So if the signal is belonging to a particular level, we will say that yes, this is the condition. All right, if that never happens, then we will take the next element. So suppose for example at this particular point we consider this as a 0 level, then maybe this particular level we consider it to be the 1 level, then 2 level, 3, 4, 5, like that it will go on. All right, so based on the level, in each level will have its own digital code. So whenever the signal is within that particular level, it will be indicated by that particular code. So for example, the 0 level will be coded as 000. All right, so that will be a 000. So 3-bit as zeros. Now suppose we have this one as 1. So in digital form, 001. So whenever the signal will be here, it will be 000. Then the next 3-bit, that is 001. Like that, so on and so forth. All right, so that is basically what the quantization is, and how the levels can also be formed. We'll discuss that in next class, and we'll continue and finish off in this segment. All right, so let me go back over here and stop sharing as well as stop recording. Thank. Let me stop recording first. Okay. All right. So we'll come back on next day's class, and we'll continue from here after.